Okay, hey folks, how we doing? So getting into this chapter 5 on simple mixtures. So I am expecting kind of a pretty quick turnaround time on this chapter because we do need to get kind of caught up. But also this is a relatively short and sweet and simple chapter. So this will be largely conceptual, not a whole lot of math from this chapter. And I doubt that I will generate any Igor activities from this chapter, but there's still some really cool chemistry going on here. So partial molar quantities. So you're already familiar with one partial molar quantity, and that's partial pressure, right? In Dalton's law of partial pressures. But something that I'm going to get into that you probably haven't talked so much about is the partial molar volume, and that is the partial molar volume from a simple mixture. So we recognize this partial molar quantity is for a simple mixture. Okay, so partial molar volume I will define as V sub J, where J is a subscript denoting a chemical identity. Okay, and because this is a partial quantity, right, this is the partial of V with respect to the partial of number of moles of species J, and this is with a bunch of stuff being held constant: pressure, temperature, and N prime. N prime meaning the total number of moles in my mixture is constant. Okay. So for example, if I have a mixture of J and K, so N prime is Nj plus Nk. So the totals of those are constant, but we recognize that I can either vary the number of moles of J in my mixture, or I can vary the number of moles of K in my mixture such that they add up to a mole fraction that's always consistent. Okay. So for example, the mole fraction of J is going to be Nj over N prime. All right. And so let's suppose that we mix species A and B together. Okay. And you can see I've got this graph of ethanol and water. So maybe A is ethanol and B is water, for example. Okay. If I now want to talk about my total change in volume of this mixture, so the total change in volume that happens when I mix infinitesimally small quantities of these two, then I can expand this as the following. So the partial volume of species A with P, T, and N, B, of course, being held constant now to make to hold that constant. Okay. And then actually, you know what? I'm realizing this is probably getting confusing. So let's get rid of this and we'll stick to this notation. Okay. So for partial of NA, we're going to hold NB constant, and then it'll be that case for the other partial derivative. Okay. And then DNA, DNA. And then now we've got the partial of V with respect to the partial of B, and now that's P, T, and N. A is being held constant. So that's where you get that overall, the total number of moles will be constant, but we're varying which one, right? A or B, okay? And so I can write this succinctly as dV equals V sub A dNA plus V sub B dNB. Okay, so these two are equivalent expressions with the way that I've written them. And what we note, as we change the amounts of A and B, the prevailing intermolecular forces of the solution change. And this leads to a different thermodynamic environment. Okay. So how does this manifest? Well, if we look at here, we've got a mixture. where there's mole fraction on the x-axis, okay? And we note here that, I'll draw a second axis above. If this is for mole fraction of ethanol, right, 0 and 1, then up top I could write mole fraction of H2O, for example, so chi. And when a mole fraction of ethanol is 0, the mole fraction of water is 1, right? And when the mole fraction of ethanol is 1, the mole fraction of water is 0. So keep that in mind when we start looking at these graphs, okay? And what I'll point out here is in the limit of only having a solution of water, right, mole fraction of 1.0, look at the value for water, 18 cubic centimeters per mole. And if you recall, we've been calculating these partial molar quantities, right? And we even did that for, mind blanking, we did that for phase diagrams, right? And so this is the same thing as when we calculated that 0.018 liters per mole for pure water, okay? And what we note now is as we start adding ethanol, there's some really interesting things that start happening, right? So there's this particularly interesting thing that's occurring at a mole fraction of about 0.1. So the water is swelling as a result. The ethanol is compressing, okay? And as we scan across here, we can see that now our partial molar amount of water is really going to diminish as it gets diluted out, which makes sense. To now the point where we have a pure ethanol solution, and we would calculate a pure ethanol solution should be 58 cubic centimeter per mole, okay? So these partial molar quantities are definitely 100% dependent on what they are being mixed with. And as a result, this is typically empirical, okay? So moving along. So now if let's say I want to make some calculations as to what the volume should be, what the actual volume of my solution should be, then I'm going to integrate from 0 to the number of moles of A, VA, D in A, okay? And then I also integrate from 0 to the number of moles of B times VB, D in B, and this just simply gets me the partial volume of A times its number of moles plus the partial volume of B times its number of moles, right? And if we expanded this into being an ideal gas, right, then we would actually arrive at Dalton's law of partial pressures, where we're just adding up the individual contributions of pressures. In this case, since we did this for a solution, or at least this example, right, this would give me the same thing, right? The amount of A times its volume plus the amount of B times its volume would give me the total volume of the solution, okay? What also becomes cool, if I go now to this partial molar quantity, and I'm going to give you an example for partial molar quantities of magnesium sulfate aqueous, which I'll remind you would be partial of V, partial of N of the number of moles of magnesium sulfate. I'm going to drop writing that aqueous because what I'm going to write in its place is P, T, and then the number of moles of H2O is constant. So this is just a really interesting example that I want to bring up here. You actually get a negative number for this one. Okay, so you actually get negative 1.4 cubic centimeters per mole at near dilute concentrations. Okay, near dilute. So what does that mean? Well, if you look at this graph right here, volume versus amount added, you notice that there are regions in which there's a positive slope, and there's some regions in which there's a negative slope. And so magnesium sulfate, aqueous solutions of magnesium sulfate, have this example where you see a negative slope for the partial molar volume. So what does that mean physically? Well, magnesium sulfate is a drying agent. Okay, so those of you that are good with your organic chemistry, remember that if you want to dry out water in a mixture, you can add magnesium sulfate, and that complexes the water, right? It makes a hydrate. So the effect of that is it actually reduces volume from our solution. For every mole of magnesium sulfate added to an aqueous solution, it will reduce the volume by 1.4 cubic centimeters, which is pretty cool, right? So again, what this means is if I had a beaker containing, let's say, 100 mils of just pure water, and now I add 1 mole of magnesium sulfate to this, I'll no longer have 100 milliliters. I'll have something like, can I do this math? 98.6 milliliters, right? It'll actually reduce the volume, which is really cool, okay? And so that's, for this number, that's in the limit of near dilution. So that's like when this is approaching the end of this curve, okay? And so now, because of all of this being empirical, there's no like definite given relationship for this solution and that solution. You have to measure it and find out. Typically, polynomials are used to fit mixtures. So in other words, like if I want to know this total volume, if I want to predict this, so you can see this equation is kind of crazy looking. So I would need to use some type of polynomial like A plus B. Let's say if I was doing this on a mole fraction graph, it would be A plus B times mole fraction plus C times mole fraction squared plus D times mole fraction cubed, etc. Okay? So there's no definite given equation for how to predict partial molar volumes of these solutions. You have to just mix them little bits at a time and look for changes in volume. And of course, then fit the data with a polynomial to get after that quantity. I'm not going to really have you do much with that, but it's an interesting example all of the same, where you can actually add a solid to a liquid and it reduces the volume. It's counterintuitive, right? Okay, so